part 3 for today's session. We've now looked at the ideal transformer. What we're going to do now is consider how we can solve some more complex problems by using the transfer and impedance method. So first part of that is to simplify the turns ratio into a single digit rather than a ratio, rather than a fraction. It simplifies the notation for the calculations that are coming up. So it's quite common to use the lowercase letter I as the transformer ratio. So what we're saying here is if we let I equal n1 over n2, and it's always that way up, you must make I equal to n1, the primary turns, over the secondary turns. You shouldn't turn up the other way. Okay? What that means is we could then write E1 over E2. We know that's equal to N1 over N2 is equal to I, and therefore, rearranging that, the primary voltage is equal to the turns ratio times the secondary voltage. Equally, we could write that E2 is E1 divided by A. Yep. All of those would be true. And because I2 over I1 is equal to the turns ratio, remember the current is up the other way, we can write that's equal to A, and therefore we can write I1 is I2 over A, and we can write I2 is A times I1. So using I to represent the turns ratio just simplifies a little bit the notation for what's coming up. Otherwise, if we left it as n1 over n2 all the time, we're going to end up squaring that value in a minute. We'd be putting brackets around n1 over n2 to put a squared sign to it and everything. Okay, so that just helps to simplify the notation a little bit. You're all happy with that? So, impedance ratio. What we can do here, as we've already said, I is n1 over n2. E1 over E2. I2 over I1. Okay? Now, what we can also say, and we said it on the previous page, E1 over E2 and 1 over A is equal to I1 over I2. Alright, now here comes the bit that might be a little bit tricky to pick up, but maybe not, we'll see. Okay, the generator just so we think to do, isn't it? The generator sees an impedance, because we've got an impedance connected here, Z, okay? But the generator sees an impedance Z dash on here, okay? And the apparent impedance is the impedance the generator thinks it's got connected to it between the terminals such that Z dash is equal to E1 over I1. Yep. This Z dash, we're going to see that a lot in the rest of this term. That's the reflected impedance. Z is actually connected to the secondary, but what the generator thinks it's got connected to it in terms of Z, we call Z dash. Yep. That's the reflected impedance, or the impedance the generator sees. On the other hand, secondary terminals see an impedance Z without the dash equal to E2 over I2. So if we go back to this formula here, I'm going to write it again. Z dash is equal to E1 over I1, okay, but we substitute in for E1 I times E2. Looking back at our statements earlier, E1 is A times E2. Yeah, so we substituted A times E2 in for that. And underneath, going from here, we can substitute in for I1, I2 divided by A. Yep. And that simplifies to that. You see where that come from or not? No. Z. Yeah. Maybe I'll have another step in there. Do you see how that becomes A squared on the top? Yeah? Do you all see that or not? Dividing by a fraction, when we divide a fraction by another fraction, we turn one upside down and multiply. So this A comes up here and becomes A squared. Yep. So that becomes A squared times E2 over I2. And what's E2 over I2? That's Z. Yeah, so it equals A squared times Z. So the impedance on the secondary, as seen by the generator, is equal to the turns ratio squared times the connected impedance. So we can summarize if we've got Z on the secondary side, it's equal to A squared times Z if we put it on the primary side. Yep. And that's what we call, this value is what we call Z dash. So any impedance on the secondary side can be transferred to the primary side and written as that impedance with a dash on it, and its actual value is equal to A squared times what it is on the secondary side. E on the secondary side is equal to what on the primary side? Right, enter. That's quite good. Remember, if the turns on the primary side are bigger than they are on the secondary, that's going to make I a whole number, and therefore the voltage on the primary side is going to be bigger than that on the secondary. So that looks right to me. Yeah? So if we're stepping down, the voltage on the primary side is going to be higher than it is on the secondary side. Yeah? And then I on the secondary will be I over A when transferred, and these will be known as, in our notation system, we're going to use E dash and I dash. We might end up with, well, we got more than one value, we might end up with subscripts as well. So the notation system is going to get a little tricky. That's why I thought we'd have a summary. So if I've got an impedance on the primary side and I want to find out what it would be on the secondary side, I'd have to divide by A squared to go back with this from an E on the secondary to an E on the primary. I'd have to divide by A, and to go back from an I current on the secondary primary to get a current on the secondary, I'd have to multiply by A. Everybody got that? Yeah? Because if you got that solid base, it makes what's coming up just that little bit easier. Okay? I was simply N1 over N2. Yeah. But as you can imagine, if we left it as N1 over N2, then when we're squaring up, would be the notation would get a lot more tricky, and there's more chance of making a mistake. All right. So 50 ohm resistor is connected to the secondary of a transformer. Oh, just go back. So effectively, once we've found that Z dash value, we've effectively taken the transformer out of the problem. We can then use this generator voltage to calculate the current flowing and the voltage here, and then transfer it back to the secondary and solve the problem, which is not needed for a basic problem. But if you've got more than one component, when we start putting our components in to represent the losses in a transformer, then we'll need to use this method to actually get the results. All right. So a 50 ohm resistor is connected to the secondary of a transformer with a turns ratio of 1 to 25. So there's our resistor, 50 ohms. I is 1 over 25. Calculate the impedance seen by the generator. What impedance does the generator see looking in there? Okay, so what we've got to use here is it wants to know what Z dash is, and from the formulas we just looked at, Z dash is equal to A squared times Z. I equals 1 over 25, which is equal to 0.04. So the answer here is 0.04 squared times 50 equals 0.08 ohms. But this is a transformer where N1 is smaller, 25 times smaller than N2. So we're talking about the voltage being higher on the secondary side than the primary side. So we expect the current to be down. Expect a high current this side, so we expect a lower impedance seen by the generator than is actually connected. So a step-up transformer makes the connected impedance look very much smaller than it actually is. Conversely, if we made that 25 to 1, that would be a step-down transformer, and it would make the impedance look smaller. Yep. You'll follow that example. Yeah? Following example demonstrates how the effective value of a capacitor can be changed using the transformer. So we've got a 10 microfarad capacitor connected to a transformer with a ratio of 1 to 5. Frequency supply is 50 Hertz. Calculate the impedance seen by the generator and the value of the capacitance seen by the generator. Okay, so quick diagram. We've got that. The connected generator. Ratio I is 1 over 5, which is 0.2, is it not? Okay. We want to calculate the impedance Z dash here. That's what we want to know. First of all, for A, how do we start that problem? So how do I do that, Matt? Capacitor into reactance. So just going to clarify what we're doing. ZC, call it ZC, is equal to XC. Yeah, the reactance. We haven't got to worry about the complex value here because we got no mixture. That's all reactive, so we don't have to worry about the angle. We're only interested in the magnitude here. Is equal to 1 over 2 pi FC, 1 over 2 times 50 times, what was the size of the capacitor, boys? 10 microfarads, wasn't it? 10 times 10 to the minus 6. The result of that is, oh, mustn't miss a pi out, Luke, must we? $318 ohms. Yep. Okay. Therefore, ZC dash, how do we calculate that? A squared times ZC, which is 0.2 squared times 318 equals 12.7 ohms. Yep. So that's the impedance seen by the generator. Does that ring true with a transformer that is effectively step up in voltage? Step up in voltage means step down in current. Step down in voltage means step up in down in current, so you'd expect a bigger current on that side. So if you're going to get a big current, the impedance must be smaller. All looks good. It's always worth thinking, does that look right in terms of the components we got here and what you know about them? B, we know that ZC dash, using the formula from earlier, is equal to 1 over 2 pi f c dash, and now we can rearrange that to find the reflective capacitance. So that goes up and the other one comes down. 2 pi f zc dash, so that's 1 over 2 pi times 50 times 12.7 equals . And I got 250 microfarads. That's A squared times bigger, is it not? No, 1 over A squared times bigger. So by connecting that capacitor to that step up transformer, it actually appears as though you've got a bigger value capacitor than you actually had. 1 over a squared times bigger. The problem there is if you think you're gaining in capacitive value, you've got to up the voltage to do it, so the capacitor's got to be of a bigger working voltage than it would be if you had a directly connected 250 microfarad one. Yep. Okay.